So, in the last lecture, we started proving Dirichlet's unit theorem. Dirichlet's unit theorem says that the group of units in the ring of integers of a number field k, so OK cross is a finitely generated abelian group, and in fact it gives a more precise statement. It says that the rank of OK cross modulo its torsion is R1 plus R2 minus 1. And to prove that, we started by defining Dirichlet's regulator map from OK cross to R to the R1 plus R2, and this sends alpha to log of mod of sigma I alpha, where sigma i's are real as well as complex places of K. And we show that image of lambda is contained in this particular hyperplane, which is given by the following linear equation: xi plus 2 times summation x j. So, I going from 1 to R1, j going from R1 plus 1 to R2. This is equal to 0, and we proved the following things. We proved that kernel of lambda is finite, and hence kernel of lambda is OK, a torsion of OK cross. And then we want to prove that image of lambda, so we proved the following, is discrete in H. And lastly, we want to prove today that image of lambda spans H. Okay. And to do that, we proved the we did the following. We want to show that if lambda 1 up to lambda R1 plus R2 are real numbers, not all equal, then there exists eta in OK cross such that this quantity f eta, which is summation lambda I log of mod sigma I eta plus 2 times lambda j summation, sorry, it should be, the summation should be outside, summation over j, this is I going from 1 to R1, j going from R1 plus 1 to R2, lambda lambda j log of mod sigma j eta, this quantity is not 0, which this will mean that image of lambda does not satisfy any linear relation except the one defining H, and hence it has to span H. And to do that, we choose rho 1 up to rho R1 plus R2 in the set of positive real numbers, such that rho 1 up to rho R1, rho R1 plus 1 squared up to rho R1 plus R2 squared, this quantity we called A, and this has to be 2 by pi to the R2 modulus of discriminant to the half, this quantity was called A. And then for S, we chose x1 up to xr1 plus r2 such that mod of xi is less than or equal to rho I as usual, and then mod of xj okay, sorry, this should not be, I think I made a mistake last time, this should have been xn, I hope I did not, but squared plus x j plus r2 squared is less than or equal to rho j squared for j between 1 and r r1 plus 1 to r1 plus r2, and I think the same thing on the previous page. Where did it go? Yeah, this should be r1 plus r2, not r1 plus r2. Yeah, okay. All right. So, by using the result on geometry of numbers, there exists a non-zero alpha in S intersected with OK, and we proved the following thing about, so using the fact that alpha is in S, we get that mod of sigma I alpha is less than or equal to rho I. This is for all I between R1 and R1 plus R2, and as alpha belongs to OK, we get that mod of sigma I alpha is bigger than or equal to A inverse rho I, but here we have to take this dichotomy into picture. So, because there are complex places, right. So, sigma I alpha is bigger than or equal to A inverse rho I squared for R1 plus 1 I and then R1 plus R2. Okay. All right. So, this is what we did last time. This is where we stopped last time. So, now let me continue the proof from here today. Okay. So, we say that two elements alpha 1 and alpha 2 in OK are equivalent if there exists a unit such that alpha 1 is equal to x times alpha 2. Okay. So, this is equivalent to saying that the two ideals are equal. The ideal generated by alpha 1 is same as the ideal generated by alpha 2. Okay. If that happens, then they will differ by a unit. All right. So, this is what we say, that two elements in in OK are equivalent if they differ by a unit. In ring theory, you may have learned this as being associates. So, if alpha 1 is associated, alpha 1 and alpha 2 are associates of each other, then they differ by a unit. In any case, we are not going to use this notion for a long time. That is why I thought I will just define it here and we will call them equivalent. All right. So, if two so if alpha 1 is equivalent, so it is clearly an equivalence relation, alpha 2, then norm of alpha 1 from K to Q is plus minus norm of alpha 2, right. So, that is because their norms differ by norm, the ratio of their norms is equal to norm of x, and norm of x on account of x being a unit is plus or minus 1. Okay. All right. So, if I consider all elements of OK with norm less than or equal to A, then there are only finitely many equivalence classes of such elements. Okay. So, so there are only finitely many equivalence classes of norm, equivalence classes of elements of lambda, of elements of OK with norm less than or equal to A, right. Remember, A was this quantity that we had before. Okay, all right. So, okay, let me just spend a minute on this. Yeah. So, if two elements are equivalent, then their norms are same up to sign, and yeah. So, the converse need not be true, by the way. Two elements can have same norm, but they need not be conjugates of each other. Okay. Nevertheless, the statement that there are only finitely many equivalence classes of elements of OK with norm less than or equal to A, this statement is true. All right. So let beta 1 up to beta n be representatives of these classes. Okay. All right. So, I know that norm of alpha is less than or equal to A, right. And so, there exist beta I such that alpha is equivalent to beta I, right. And this means that eta, which is alpha by beta I, this is a unit. So, we have constructed a unit, right. Now, this unit of course may not be the unit that we want, because we still have not made good choices of these row i's, and that is what we are going to do next. We are going to make good choice of row i's. So, if you look at f of eta, then this is equal to f of alpha minus f of beta I, right. So, let me remind you what this is. This is lambda 1 log mod sigma 1 of alpha, so on, lambda r1 log mod sigma r1 alpha plus 2 times lambda r1 plus 1 log mod sigma r1 plus 1 alpha, so on up to 2 times lambda r1 plus r2 log mod sigma r1 plus r2 alpha minus the same thing now but with beta I is log of mod sigma 1 beta I lambda r1, sorry, the minus sign is all outside a bracket beta I plus 2 times lambda r1 plus 1 log mod sigma r1 plus 1 beta I. These things are just notationally very heavy, they are not difficult, they are just notationally cumbersome. Beta I, okay. Now, what I want to do is I want to take the difference of this. So, I want to consider f of eta minus a quantity which is kind of independent of any element, which is lambda 1 log of rho 1 and so on up to lambda r1 log of rho r1 plus 2 times lambda r1 plus 1 log of rho r1 plus 1. Remember, all these rho i's are positive real numbers. And so you do not have to take modulus of those things, rho r1 plus r2, right. So, our claim is that this quantity, yeah, I should have written this on the next page. Oops. Yeah, maybe I will write it again here. So, I want to consider f of eta minus lambda 1 log of rho 1 so on lambda r1 log of rho r1 plus 2 lambda r1 plus 1 log of rho r1 plus 1 plus 2 times lambda r1 plus r2 log of rho r1 plus r2. My claim is that this is at most equal to f of beta I or mod of this plus log a summation lambda I, okay, mod of lambda I going from 1 to r1 plus r2, and this quantity let me call it b. Okay. And why is this true? Well, you just write down the expression for f of beta, and then you know that each of these you use the fact that each of the elements log of alpha I, log of sigma I of alpha is bigger than or equal to log of A inverse log of rho I, and you just do this. So, this is kind of an easy exercise in manipulating things. So, but the relevant point is that this quantity is independent of rho i's, right. Okay. So, now what you can do is you can choose your rho i's. So, here is a slightly tricky claim, but once you get the right idea, it is easy. So, I will tell you what the right idea is. So, choose rho i's such that right, such that this quantity that we are subtracting from f of eta, so lambda 1 log rho 1 and so on, lambda r1 log rho r1 plus 2 times lambda r1 plus 1 log of rho r1 plus 1 and so on, plus 2 times lambda r1 plus r2 log of rho r1 plus r2 is, so mod of this is bigger than b. And how do we do this? So, this kind of seems tricky, but let us say, so I will just tell you what the right idea is. So, let us say that lambda 1 is bigger than lambda 2. We can always arrange for such a thing, right, because they are not all equal, we can maybe renumber them. Okay. And so, whatever lambda whatever the expression is, it will be dominated by the rho 1 term, right. The rho 2 term will not dominate it, and so we can take all rho I is to be equal to 1 for I bigger than 2, and yeah, for the other thing we just take yeah, so what was the expression that was needed? Right. So we want to have rho 1 times rho 2 to be equal to A, right, and so we want rho 1 times rho 2 is equal to A, and so we can write this as lambda 1 log rho 1 plus lambda 2 log rho 2. You can rewrite this as lambda 1 rho log this minus lambda 2 log rho 1 plus lambda 2 log A. So we forget about log A for the moment, I think, and we just write lambda 1 minus lambda 2 log rho 1, right, plus lambda 2 log A, and now we can, so lambda 1 minus lambda 2 is positive, and we can make rho 1 as large as you want so that this quantity is bigger than A. Okay. So that is the relevant idea. You will have to take a few cases to take into account that maybe R1 is 1 or all the lambda 1 up to lambda R1 are equal, and then the unequal quantity can be found in the other lambdas and so on. So you may have to take a few cases, but this is the idea. Okay. And so it's not very illuminating to dwell on this idea, but you can choose this. So once you can choose this large enough, you get the following, right. So what you have is f of eta minus this, yeah, I have written this again and again. So let me call this quantity d minus d is less than or equal to b, but mod of d is bigger than mod of b, hence f of eta cannot be 0, and that is what we wanted, right. So that is what we wanted. Okay, so that proves Dirichlet's unit theorem, amazing, right. So we have proven second important theorem of our course, Dirichlet's unit theorem. So let me give you a corollary of this one, and let's discuss an example or two. So before moving on, let's discuss example. Okay, so first of all, what does it say about Q? And we know this, right. So we know that Z cross is plus or minus 1, and so rank, so torsion of Z cross is equal to Z cross itself, of course, right. So rank of Z cross modulo its torsion is 0, which is R1 minus 1, right. R1 is 1 in this case and R2 is 0. Okay. So that is just a sanity check that Dirichlet's unit theorem is what you should get for Z. Now if K is an imaginary quadratic field, then OK cross, again what is R1? R1 in this case is 0, R2 in this case is 1, and so if you take rank of OK cross modulo its torsion then this is equal to 0. So, these are the only two examples of number fields in which the rank of the unit group, whenever I say rank of unit group and do not say torsion, I do mean modulo its torsion, but I will not say it again and again. So, these are the only two number fields in which rank of the unit group is 0. Okay. And units are what cause a lot of difficulty when you want to solve equations, right, because you understand prime ideals or ideals well, and equality of two ideals, equality of two principal ideals means that the generators of those principal ideals differ by a unit. Now, if there are only finitely many units, you can try to handle them in some way, right. For example, in Z we just have 1 and minus 1 as units. So, if you fix a sign, then you handle it in a certain way, right. And so, if you have finitely many units, you can there are ways to handle them very easily. But if there are infinitely many units, equality of ideals does not tell you a lot about the generators of the ideals, and that is what makes it very hard. So, these two number fields are very, I mean, in some sense easiest to study, and so this is why these two number fields have a very nice explicit class field theory, etc. Okay. Already if you go to K as a real quadratic field, then R1 is 2 and R2 is 0, and so rank of OK cross modulo its torsion, this is equal to 1. Okay, so already OK cross is an infinite group. So, let us look at Q square root of 2. Okay. Now, in this we can have the following. In this we can have alpha to be square root of 2 minus 1, and you can see that alpha bar, this is square root of 2 minus 1 times square root of 2 plus 1, which is equal to 1. And so, alpha is a unit, and you can show. So, here is an exercise, I think this is true, I am going by on a limb here, that OK cross modulo its torsion is generated, it is a infinite cyclic group, right, and I think it is generated by alpha. All right. So, yes, so there are these ways in which we can compute the unit group explicitly, and if the unit group has rank 2 and so on, it becomes slightly trickier to compute it explicitly, but there are algorithms to do it. All right. So, that is so much for examples, and we will look at more examples later on. Now, here let me give you a corollary of, but before that I have to define something. So, let S be a finite set of primes of OK, prime ideals. So, prime. So, this means non-zero prime ideals. Okay. So, S is, let us say, P1 up to Pt. Okay. This is my set S. Then I define OS to be the following thing. This is all alpha by beta in K such that beta does not belong to P for any prime P not in S. Okay. So, the only things that can appear in the denominator are elements whose ideal contains only P1 up to Pt in the prime factorization. Okay. So, for example, Z P, this is equal to A over P to the power R, such that A is in Z, and R is a natural number, including 0, of course, right. Okay. All right. So, so the corollary of Dirichlet's unit theorem is the following. OS cross is a finitely generated abelian group, and rank over Z of OS cross modulo its torsion is equal to R1 plus R2 minus 1. So, this is the component that was there before plus the number of elements in S. Okay. All right. So, how do we prove this kind of thing? So, let me give you an idea of how this is proven. So, what you do is you look at, you consider the exact sequence which goes from OK cross to OS cross. So, there is an inclusion like this. Every unit in OK is also a unit in OS. So, this is clear, and then you go to the free abelian group generated by so let me write it like this, since we have numbered our set S, this. Okay. All right. So, what so this map is maybe I have to define. So, how is this map defined? So, let me take alpha in OS cross and I look at the ideal generated by alpha. This will this will contain some okay. So, the numerator can have various things, but the denominators will have anyway. So, what I will do is I will write it like this. So, P1 to the N1 up to Pt to the Nt, and then some ideal A. So, A is an integral ideal co-prime to P1 up to Pt, okay. And so, then alpha will go to N1 up to Nt, okay. Now, this last map is not quite surjective, but here is an exercise. It uses finiteness of the class group, is that this map phi, so co-kernel of phi is finite, okay, and hence you get that rank of OS cross modulo torsion is equal to rank of OK cross mod torsion plus T, because the image of phi will have rank T. Okay, so that is how you prove this. Okay, so we have proved Dirichlet's unit theorem, and we got a little bit more out of it. We got rank of OS cross for certain localizations of OK, right, called OS. Now, we want to use these two theorems to do actual computations, and for that we need to understand how primes in Q factorize in a number field, what happens to elements in Q when you look at them as elements in bigger fields, etc. And in that context, it's easier to just study relative extension. So, rather than studying K over Q, we can study K over F for two number fields F, and it is no more difficult than studying K over Q. So, from the next lecture we are going to study these relative extensions of two number fields, and we will see how we can pass from ideals of one to another, going up and going down, etc. So, that is what we will do next time. Thank you.